Hi, this is Guo-Hua Wang from Nanjing University. I would like to introduce our paper, Practical Network Acceleration with Tiny Sets. The paper tag is Thursday AM 366. This paper aims at solving the problem how to accelerate deep networks with a tiny training set. In this paper, we claim dropping blocks is an embarrassingly simple but powerful few-shot compression method. Given a deep network, some blocks are dropped to reduce its latency. Compared with pruning filters, dropping blocks enjoys higher acceleration ratio and better latency accuracy trade-off. Next, we propose a new concept named recoverability to measure the difficulty of recovering each block, and in determining the priority to drop blocks. Finally, based on dropping blocks and the recoverability concept, we propose the practice algorithm, which is a powerful few-shot compression method. Our practice achieves extraordinary performance and significantly outperforms previous few-shot compression method. And it is also versatile and widely applicable for different network architectures. Next, I introduce more details of this paper. To accelerate deep networks, many network compression methods have been proposed. However, most previous methods rely on the original training set to recover the model's accuracy. But, to preserve data privacy or to achieve fast deployment, only scarce training data may be available in many scenarios. For example, a customer often asks the algorithmic provider to accelerate their CNN models, but due to privacy concerns, the whole training data cannot be available. Only the raw uncompressed model and a few training examples are presented to the algorithmic provider. In this few-shot compression scenario, most previous works adopt filter-level pruning. However, it cannot achieve a high acceleration ratio on real-world computing devices. To make compressed models indeed run faster than the uncompressed models, lots of flops are required to be reduced by filter-level pruning. And without the whole training dataset, it is difficult to recover the compressed model's accuracy. Hence, previous few-shot compression methods often exhibit a poor latency versus accuracy trade-off. Another problem is previous works focus on the FLOPS accuracy trade-off, which is a misleading metric for few-shot compression. In practice, we are more care of the model's real runtime on devices. Hence, we argue that the latency accuracy trade-off is a better performance metric for few-shot compression. In this paper, we reveal that block-level pruning is fundamentally superior in the few-shot compression scenario. Compared to pruning filters, dropping blocks enjoys a higher acceleration ratio. As shown in this figure, with the same flops reduction, dropping blocks outperforms all other pruning methods and achieves the lowest latency. Therefore, it can keep more capacity from the original model, and its accuracy is easier to be recovered by a tiny training set under the same latency when compared with filter pruning. Dropping blocks also enjoys high accuracy. This table reports that an embarrassingly simple baseline has already surpassed existing methods which use complicated techniques. The baseline, BP, blocks, simply removes the first few blocks and fine-tune the prune network with the cross-entropy loss. To further improve dropping blocks, we study how to choose blocks to drop. Different from previous works that neglect the fine-tuning process, we argue that an effective metric should be consistent with the fine-tuned accuracy. To this end, we propose a new concept, namely recoverability. Recoverability measures the ability of a pruned model to recover accuracy. Here is the framework to compute the recoverability. One block is dropped, and adapters are inserted around the dropped position to alleviate the loss from dropping this block. Note that all adapters can be fused in the neighbor CONV layers while keeping the outputs unchanged. That means these adapters will not be overhead to the pruned model. Finally, the L2 distance of pruned and original networks features is computed as the recoverability of this dropped block. Surprisingly, we empirically find optimizing only adapters is close to optimizing all parameters under the few-shot setting. Hence, it results in an excellent metric to predict the accuracy of the fine-tuned model. Thanks to the limited computations and parameters in adapters, calculating the recoverability requires only a few training samples and little training time. Finally, we propose the practice algorithm, standing for practical network acceleration with tiny sets of images. Practice calculates the acceleration ratio and the recoverability of each block. Then it drops several blocks with small pruning scores. And finally, the pruned model is fine-tuned on the tiny set with the help of the original model. Our practice achieves the extraordinary performance. For 16% latency reduction, practice surpasses the previous state-of-the-art method on average by 6% top 1 accuracy on ImageNet. And for 22% latency reduction, practice outperforms SOTA on average by 7% top 1 accuracy. This figure summarizes the data latency accuracy trade-off achieved by our practice. With less latency reduction, the accuracies for different amounts of training data are comparable. But for a large latency reduction, it is challenging to recover the accuracy by only a tiny training set. Our practice can also accelerate MobileNet v2 and outperforms previous methods by a significant margin. In some extreme scenarios, not even a single original training sample is to be provided. Zero-shot pruning is required. Because practice does not need ground truth labels, it is able to accelerate networks with the images synthesized by data-free knowledge distillation methods. We adopt synthesized images produced by ADI as the training set. For both ResNet 50 and MobileNet v2, our practice achieves higher top 1 accuracy with more latency reductions. Another choice of zero-shot pruning is collecting out-of-domain training images. Our practice is also robust to work with these data. The accuracy is boosted by using more training samples and even close to that of using original training data. At last, we make conclusions. In this paper, we argue that the FLOPS accuracy trade-off is a misleading metric for few-shot compression and advocate that the latency accuracy trade-off is more crucial in practice. We are also the first to reveal dropping blocks' great potential in few-shot compression. We propose a new concept, recoverability, to measure the difficulty of recovering each block, and in determining the priority to drop blocks. Then, we propose practice, an algorithm for accelerating networks with tiny sets of images. Finally, our practice achieves the extraordinary performance. That's all. Thank you. There are links of our paper and code.